Hey everybody, Jonathan here. In this video, I will be giving you my take on section 7.1, which is about an integration technique called integration by parts. Now, in chapter 7, we're going to be learning lots of integration techniques. However, the two main integration techniques that we'll be constantly falling back on again and again are integration by substitution, which we saw back in section 5.5, and integration by parts. Now, the integration by parts formula says that the integral of u dv is equal to uv minus the integral of v du. So this means when you're applying this to some integral, you have to make two choices. You have to choose u and you have to choose dv. So in this video, I'm going to be going over strategies on how to choose the right u and dv. So the first thing, if you're going to use it to integrate some function f of x dx, you absolutely have to choose u and dv such that f of x dx is u times dv. So for example, you might confuse it with substitution. In substitution, you want to let u be like a denominator or what's inside something. Here, that's no longer a choice. F of x dx has to be u times dv. So that means u could never be something inside the denominator. It could never be something inside a square root, because those choices will make it so that the entire integrand is not u times dv. Now, your choice of dv is going to be a little more limited because you have to choose something for which you know its antiderivative. The way integration by parts works is you choose a u, you choose a dv, you differentiate u to get du, and you integrate or antidifferentiate dv to get v. So if you're choosing a dv for which you don't know the antiderivative, you're not going to get anywhere. Now, the lovely thing about integration by parts is it replaces one integral, the integral of u dv, with an expression containing a second integral, the integral of v du. However, this can always be done in some sense, but it will only be useful when you have a better chance of integrating the integral of v du than you did with the integral of u dv. So your choices are only helpful if you either know straight away what the integral of v du is, or in some sense it's simpler than the integral of u dv. So now I'm going to give you some strategies for how to actually make these choices. So ideally you want to choose u such that du is simpler than u. However, this is not always possible. So really good choices for u when they're possible is any polynomial, because then the derivative has a smaller degree and is therefore simpler, or natural log of x. In fact, natural log of x is an amazing choice because natural log of x is a very complicated function, but its derivative is 1 over x, which is much, much simpler. And other choices you sometimes have to make for u are e to the x, cosine x, or sine x. These choices aren't great because when you differentiate these three functions, you get something with the same amount of complexity, but sometimes it's the best you can do. Now we can see how these choices play out in example 1 in the book. To find the integral of x sine x, a great choice for u was x, because the x is a polynomial and its derivative is really simple. The derivative is just 1. And sine x is a decent choice for v because we know its integral. We also see these principles being applied in example 2, where they calculate the integral of natural log of x, which is kind of exciting because integral of natural log of x, it's a basic function we didn't know the integral of before. And before we knew integration by parts, we couldn't find it. However, since natural log of x shows up, you should try to make sure to let u be natural log of x and see where that leads you. And in this case, you quickly get the integral. Now, point 5 almost feels like cheating. It is always an option to let dv equal dx, because then the integral of dx is just x. And then du has to be everything else, but we can find any derivative no matter what. So it's always a choice, and especially if your function, there is no other possible thing to try, it's something to give a shot with. In fact, the example 2 we already looked at, u was natural log of x and dv was dx, and things worked out great. And something similar happened in example 5. In example 5, there is no interesting way to have this be u dv except to have u be tangent inverse of x and dv be dx. However, that's exactly what's necessary in order to find that integral. Now my point 6 is sometimes you just have to try different choices for u and dv and see what develops. Sometimes there is going to be more than one choice, and sometimes it's a complicated integral where you can't necessarily see what the end game is going to look like. So you try stuff and see where it leads you. And furthermore, it might take several iterations to get the answer. You do integration by parts not just once, but several times to solve a lot of integrals. Remember, you're trying to find this integral of v to u at the end of the game. It's a different integral than the integral of u dv, and you can always try integration by parts on the integral of v to u. As a general rule, so long as the integral of v to u is simpler than the integral of u dv, you've made progress, and you should keep going with that. Now, this is illustrated in example 4. In example 4, letting u be t squared is a great choice because it's a polynomial, and then dv is forced to be e to the t dt, but that's okay because we know that integral. And you go through the integration by parts process, and you wind up having to know, in order to solve the problem, you have to know the integral of t e to the t dt. However, we started with the integral of t squared e to the t. We now have the integral of t e to the t dt. That means things have gotten simpler and we've made progress. And by doing a second iteration, and usually we recycle the u and dv, keeping in mind they mean something different in this part of the problem than they meant up above, we do the process a second time to find the integral of t e to the t, and where we let u equal t and so on, and we'll get our answer. Now, in the toughest integration by parts problems that you're likely to be asked, it's going to come out that you're going to go through several iterations and you're not going to get an answer, but eventually you'll notice the original integral appearing. When the original integral appears, so you go through the iteration several times, and after several iterations you've got the integral of v to u, and that at that iteration it equals the original, whatever the original choice was for u, the integral of u dv, then you have an equation where you can solve for that original integral to figure out the answer. So this is never super simple, but the book did do an example of this in the integral of e to the x sine dx on example on page 474. Now in this example, their first choice was to let u be e to the x and dv be sine x. And then after calculating everything, they got the integral of e to the x sine x dx was e minus e to the x cosine x plus the integral of e to the x cosine x. So on the second iteration of integration by parts, they let u equal e to the x and dv equal cosine x. And plugging everything, and then when they calculate integration by parts on that integral, they get that it is equal to e to the x sine x minus the integral of e to the x sine x dx. And when they plug that into this integral here, they wind up with this equation. The integral of e to the x sine dx equals minus e to the x cosine x plus e to the x sine x minus the integral of e to the x sine x dx. Notice that this integral has appeared twice. And since it's appeared twice, you can treat it like a variable and just solve for it to get the answer, which is what they do. Here they've solved for it and they get their final answer. Now these tips are really just to get you started. As you grow in confidence, you'll be more willing to just try stuff and see what happens. In fact, a lot of the stuff we do in Calculus 2 is so much more interesting than stuff in Calculus 1 because you don't know what you don't necessarily know if you're going to get the final answer. It's like you're trying stuff, you're exploring stuff, and that actually makes the math a lot more fun. So I hope you all have fun with these problems.